Well, good afternoon. Though it's really more good lunch, I guess, or good noon. Uh, anyway, haven't been on the channel for a while, but I guess I just had other projects that weren't worth recording. But I did want to record this because hopefully it'll be a simple fix. What I have here, and I've had this on the channel before, is my 11683A range calibrator. And you use these devices to calibrate a power meter like my 435B here. This is a classic design power meter. I just love that form factor. Anyway, basically what this acts like a sensor head, and you can plug into the power meter, and then on this dial here you can set the various ranges, and you can confirm that you get a full deflection reading on the meter when it's set correspondingly. So that's the whole point of the range calibrator. Now, the reason that I got my range calibrator out is I just acquired a couple of HB5347A frequency meter, power meter combos. And I think I might do a video on those because they're an interesting just combination. They were made for mobile use, like in the cable industry or the cell tower, the cell phone, mobile phone industry. And they're designed to be portable and can be run off battery power. But I bought a couple of these. Wanted to give one to my dad because he blew the sampler in his. And as part of that, I wanted to check that their power sensors were, working, that you could actually get power. So I grabbed the range calibrator, put it on, and discovered that the range calibrator doesn't work. So, got to take a look at it. So let's do that. Okay, so I've already unscrewed some of it to get ready. So let's take the lid off here. And let me grab my little pointy stick. Now, I showed the inside of these before, but just for a quick recap. So how they basically work is you have AC power coming into here that then hits a transformer here, gets stepped down, and then goes over to the power supply board, is rectified, filtered, and then hits a regulator before being sent back out to the unit. Now, this is going to be what they refer to as a reference output. So basically, this is a 15.8 volt DC reference output, and that's what's used in the meters in the sensor head. So when you get a full scale deflection at 100 milliwatts, I think, you should basically be getting out the back here, on the back of the unit. If we just take a quick look, you'll see there's a DC reference output. This is an output where you can use a accurate multimeter to have a look at the actual volts that are coming out of the back. So you should get 15.8 volts out there. And then as you step down through the ranges, you'll get a different voltage reading out of the back, and the aim for that is to be able to see exactly what is being fed into the meter. So that's the power supply that comes here, and then it goes into a precision resistor divider network, and these resistors are designed to achieve that voltage that's needed to simulate the various ranges. And these are all 0.1% resistors on a switch, and you can see if you have a look, we have a look at the, you can see how it steps down through each position, and it adds more resistors to the voltage dividing network. And then finally, that value is fed out to that reference, that multimeter output, the DMM output on the back, and then comes across, and if we have a look here, you can follow the orange wire there, comes into what is in fact, you can sort of, oh, that's just a plastic thing. You can see a what looks like a power sensor. And if we have a look, you'll see the power sensors that HP makes or Agilent makes or Keysight makes. They're basically this form factor. And what they've done is they've taken a power sensor and removed the thermocouple aspect of it. And they just use the FETs in there just like you would when it reads the thermocouple and then basically chops the signal up and returns it to the power meter for its analysis. The areas that it can go wrong is going to be in the power supply, here in the resistor divider network, power supply here, or balancing the FETs. Now, I hope to God that it's not in the resistor divider network, because that's a pain in the ass. You've got to get the right resistors. You've got to make sure that the values match. And I hope that the problem's not in the sensor head, because balancing the FETs and so on is quite difficult. As an aside, you can make a your own version of this, because fundamentally this is all it is: resistor divider and that sensor head. There are any number of blown sensors that are on eBay that you can get access to. And often the thing that blows is the thermocouples that are at the front of the sensor. The rest of it is typically okay. So if you can find a blown one, you can come back and start to actually just rebuild this this network. So here's the layout. Now, I put aside somewhere, when I opened it up, so I wanted to show you. I don't know what I've done with it. I've probably knocked it on the floor now. A little piece of wire fell out that was soldered. It looks like it's off, one of these type of connections where there's more wire. So hopefully that didn't come from anything terribly important. Anyway, I've taken it out, and now let's take a setup. We'll have a look at the voltages in the power meter, in the power section. So we'll start up here, and we'll have a look at this this power section. So let me get that ready, and then we'll go take a look at that. Well, before we jump in and start probing, let me show you some of the values that we're going to get. This is the schematic that is in the manual. Okay, my doggies are, somebody outside is clearly not doing things that they like. Drink of the day, because it's noon, is a coffee. I'm going to go out to lunch after this. We'll have a more interesting libation then. Anyway, coming back to the schematic, you're going to feed in your AC power, rectify it, and then the first thing to measure is the voltage across the capacitor there, and make sure that it hits 33.4 volts, which is written here. Then we'll take a look across the supply and see that we get our 15.8 volt DC output. Now, the switches on the front basically allow you to reverse the polarity. That means that instead of getting 15.8, you get minus 15.8. And then it lets you put the unit in operation, so it'll connect the power, or it'll connect the output to ground. This whole power supply here is floating. And so when you flip switch 1, you can change where the ground point goes. So in normal mode, that ground point is on the bottom of C1. So from reading from here, we should be able to read 15.8 and 33.4. And if we flip that around, we should then get minus 33.4, I guess, and then minus 15.8. I've never used this in the reverse polarity. There's no equipment that I've seen in the manual that says use reverse polarity. So I'm assuming there must have been something, or maybe some competitor hardware that utilizes it. Don't know. Utilize the Calibrate standby quite often, though. All right, so now that we have a basic understanding of where things are, let's take a quick look at what the various parts are. And I've put this image together just to make it easy to identify. So we've got CRs 1 to 4, which form our bridge rectifiers, capacitor 1, and then we have R1 to adjust the output, 2, 3, 4, and C2. You saw those when we looked at the output here. So the reference output is pulled off here. This is a current sense resistor, and this is helping the inverting feedback part of the loop to get our right value there. And then you can see switch 1 here is a double pole double throw, and the switch 2 is a single pole single throw. It has a look like somebody poked in there at some point, but none of the components seem new. So let's turn it on and take a measurement. Use my trusty fluke here. We'll just turn it on. Yep, the light's on. And so now we want to measure across C1. Yep. Yep. Okay, so we're getting 31 volts, so that's a little low, because they say it should be 33.4. Let's take a look at the output, which is the red wire here. That's 15.83. That's this is only a 4-digit meter, so that's not too bad. That's, you know, probably very close to what you'd be doing to. So let's measure, make sure that it's coming through to the resistor network. Yes, it is. And then let me see if I can get down into the output of that back end, and 14.5. Okay, so that seems to be good. Let me turn this off. Just flip this over to ohms. And now let's just check the resistor network. So we'll go down here again. That should be very low. Yep. A little low. Okay. So, let me power it on. Let me plug in my other, let me put my external 5.5 digit or 6.5 digit or 5.5 digit meter on it. We'll just grab, that's a Rigol DM3058. And let's turn that on. Okay. So it's showing 3.3 of a volt. Okay. So we did get the voltages all the way through. Let me just, one last thing. Let's put, so this should be referenced to ground. So let me just drop in on that pin again there. Yep. That should be the output. Make sure it's voltage so we don't blow anything up. Let's turn this on again. And let's check that reference to ground. Okay. We're not getting anything there at all. So am I getting, okay. So I bet if we turn that off and let's just select continuity. Yep. And check to the switch. So you can't really see what I'm doing here, but what I'm checking, let me show you here, is this middle piece is the common, and one side of this switch should be connected to the ground point here, and then when you switch it, that ground should go through to the common. And so what I'm seeing there is that it's not coming through to the common. Okay, let me try the switch again. All right, well, that seems to point to the switch being the issue. So let me grab a couple of mini grabbers and jumper the circuit, because we're not changing the switch. The switch doesn't change during operation except to turn it on or off. So we should be able to, if we take a look at the schematic again, I should be able to simply connect that point there directly to ground, which will achieve the same as S1 connecting that to ground. And then I should be able to connect the output of here on R2, which is this guy, so it's going to be there. So we'll connect ground here and the output there. And I should just be able to jumper from here to here and have it work. So let me just connect those and see how we go. Okay, so here we have it set up. So I've hooked up here to one of the ground points. They're all linked together to the chassis ground through here. You can see the black wires that come down here and then come up here. And then I've just jumped straight from here to the output. So this should make it work successfully. So let's do that. Turn it on. No smoke. Let's get some voltage in there. And now I should be able to come in on that center pin there and just ground to the chassis. And there we go. We get 15.83 volts again. So now that looks pretty much like the culprit is the switch. Let's just cable it into a power meter and make sure that it actually does work. And we'll see what happens. Okay, so here I have it cabled through to that. I have it set for, you can see on the range here, I have it set for 1 milliwatt, 0 dBm, and I have it set here. So if we just turn this on, we should see a full scale. I'm not going to bother with calibration and zeroing and everything. Okay. Well, in fact, we do see scale change there. Let's go to 100 milliwatts. And we're hitting the same point. So let's go back to, now what this goes down to -25. So let's go to 3. Let's set that. And yeah, so there we go. Seems like this guy here, S1, double pole, double throw, probably $4 to $5, is the culprit. That's a good thing to do. I now, however, have absolutely none of those. So I'll have to go order one, and in part 2, we'll just very quickly whip the switch out, put a new one in, test it, then I can move on. Probably have to recal the whole thing again, but otherwise, should be good to go. Anyway, I hope you found that interesting, and I'll catch you in the comments. Thanks very much.